We're going to do one more example of Bayes' theorem where we actually calculate some probabilities using some numbers, and we're going to do this using the scenario of taking a trip to a doctor's office. So let's say that there is some disease that is rare, and we're going to say the probability that prior probability that anybody has the disease walking in off the street is going to be 1 in a million. Okay, so that's a rare disease, and there are certain symptoms for this disease, and whether you have the symptoms or not, well, let's say the symptoms are the same as some of the other diseases that are out there that are not this disease, so similar to the common cold or something like that. And so let's say you go into the doctor, and the doctor says, I think maybe you have this disease. We should run a test to determine whether you have the disease. And so he takes a sample of saliva or blood or whatever it is, and you need to ask the doctor what's the accuracy of the test. And if he can't tell you how accurate the test is, then probably you want to get a second opinion on this. But if he does know, he should be able to tell you the sensitivity, which says the probability of a positive test result given the disease. And let's say that this is 99%. In other words, if you have the disease, the probability of a positive test result is 99%. That's pretty accurate. But there's another measure of accuracy called the specificity, which says what's the probability of a negative test result given that you don't have the disease. And this is not always going to be the same. In fact, let's say that it's 98% in this scenario. So these are just numbers that I made up. You probably will be hard pressed to ever find tests that are this accurate, but nonetheless, let's hypothetically assume that we do this. So you might ask yourself, what's the probability that somebody has the disease given that they get a positive test result? So the doctor says, let's take the test. You do the test, it comes back positive, and now you have to ask yourself, do I have the disease? Because I have a positive test result, what are the chances that I actually have this disease given this information? So we can use Bayes' theorem to calculate this, and before we do that, I'll just point out that most people think that when there is a positive test result, you've got the disease. All right, so if you go, your doctor says, yep, came back positive, we better start treating you for this disease. If it's cancer or something that takes a drastic treatment, then you might want to think about getting that treatment done before you actually do, because let's find out this probability. Probability of the disease given a positive test result. Using Bayes' theorem, that's just the probability of a positive test result given the disease times the prior probability of the disease. All that. And then we're going to divide that by the probability of a positive test result. So to find the probability of a positive test result might be a little bit tricky, but not too bad. So let's write this out. Probability of a positive test result is going to be equal to the probability of a positive test result given the disease times the probability of the disease plus the probability of a positive test result given no disease times the probability of no disease. So in other words, there's two ways to get a positive test result. One is when you have the disease, and one is when you don't have the disease. So if we were to draw a tree diagram here, we would say either you have the disease or you don't have the disease, and then we would say you get a positive test result or a negative test result, positive or negative. So we know all of these numbers actually. The probability of a positive test result given the disease is 0.99. The prior probability of the disease is 1 over a million. And the probability of a positive test result given no disease can be found using the law of complements. And that's 2%. And the probability of no disease is 1 minus 1 over a million, so that's 999 divided by a million. So when we plug all these numbers in to our computation device, in this case we're going to use Excel, we're going to get the following. We'll say P of positive given the disease. We've got P of positive given no disease. I'm going to write that as D prime. And so this is, what do we have? Probability of positive given the disease. That's the sensitivity is 0.99. The 1 minus the specificity is 0.02, or the probability of a positive test result given no disease. We're going to say what's the prior probability of the disease and the prior probability of no disease. This is 1 divided by a million. Put an equals sign in there. And then we're going to say 1 minus that to get the prior probability of no disease. Okay, so then to get the probability of a positive test result, we're just going to take these things and multiply them together. So this is going to be equal to this number times this number plus this number times this number. So the probability of a positive test result is just about 2%, which makes sense because we're saying that we have a 2% probability of a positive test result given that you don't have the disease. And the probability that you don't have the disease is almost 1. It's 99.999999%. And the probability of a positive test result given no disease, or given the disease, is 99%. And the probability of having that disease is this 1 in a million number, so very small. So we have the probability of a positive test result is equal to 0.020001. Yes, 3 zeros here. Okay, so of this little over 2%, the question is how much of that comes from having a positive test result given the disease. So this number is going to be equal to 0.020001, and that's going to be divided by, or divided into 0.000001. Yeah, that's so that number times 0.99, which is equal to 0.000099. Actually, there's another 0 in there, divided by 0.020001. So what's the probability of a positive of the disease given a positive test result? If the prior probability is really 1 in a million. Well, let's come back over here and figure that out. So here we've got probability of disease given a positive test result, and that's going to be equal to this number times this number divided by this number. So it looks like that probability is very small, almost, well, let's write down what it is. This is 0.99. 1, 2, 3, 4, 5, 4, 9. Yeah. So given a positive test result, the probability that you actually have the disease is so small that I don't know anybody that would risk any amount of money or happiness or future longevity, anything like that, on an event that has that probability. And so when your doctor says, oh, positive test result, looks like you've got the disease, you should say, well, what's the probability that I have the disease given that positive test result? And if he can't tell you what these numbers are and what this number is, then you need to go get a second opinion. Now, the reason that you go to a doctor and the reason that you listen to a doctor is because they're supposed to know what these things are. And especially this one. This is called a prior probability. And if you have a good doctor, you can say, well, what's the prior probability? They have a different term that they call it in medicine. But what's the probability that I've got the disease? And the doctor is supposed to be able to come up with a number for this based on their expert opinion. That's why you're going to see them, because they're supposedly an expert in these diseases. They look at the symptoms, they look at the lab work, listen to your story about how you got to be sick and so forth, and they're supposed to be able to revise this value. So this number is very, very small, and if it's an extremely rare disease like this, 1 in a million, what's going on here? Why is this number so small? Well, if you had 1 million people, I mean, let's think about where these positive test results come from. If you had 1 million people, how many of those would have the disease? Well, it'd be just one person with the disease. And what's the probability that you're going to have a positive test result for that one person? Well, it's 99%. So of 1 million people, you're going to have basically one positive test result. And of the 1 million people, how many don't have the disease? Well, almost all of them, 999,999. Well, so let's say that's basically 1 million. And how many of those people are going to get a positive test result even though they don't have the disease? Well, it's 2%. And 2% of 1 million is 20,000. So we're going to have 20,001 positive test results, roughly. And based on those 20,000 test results, 20,001 positive test results, how many of those came from somebody that has the disease? Well, there's just one of them. So basically we're looking at 1 divided by 20,000, and that's going to give us our probability. Okay, so the value in going to the doctor is getting his assessment of this prior probability, and everything else is kind of the same. So we could redo this calculation very quickly and easily by saying, well, what if the doctor says the probability of having the disease is 1 in 10 instead of 1 in a million? In other words, he looks at your symptoms, he takes everything else into account, and he says, I think the probability is 1 in 10. So we can redo all of these calculations, but using 1 in 10, so we have 0.99 times 0.1 divided by 0.99 times 0.1 plus 0.02 times 0.9. Right, this is the probability of a positive test result given no disease. This is the probability of no disease according to the expert. And so we can calculate that very easily if we come back over here. All we have to do is change. So let's copy all this, paste it here, And all we have to do is change the probability of the disease and say that's equal to 1 divided by 10, and everything else is going to be calculated for us automatically. So the probability of a positive test result anytime you send a sample in is going to be 11.7%. Posterior probability of the disease given a positive test result is 84%. And you could do that same thing over and over and over again. And all you have to do is change the probability of of having the disease, the prior probability. Let's say it's 0.5. If it's 0.5, then you would say probability that you have the disease given a positive test result is 98%. So these numbers here, these priors, are very, very important. And again, that's why you go to the doctor, because he's an expert. He's been trained in this stuff. He's supposed to be up on what's currently going on with the disease, with flu and whatever is going on. And so you go there for his good opinion, and if he can't substantiate his good opinion, then maybe he's not the type of doctor, he or she's not the type of doctor that you want to be dealing with. So that's another example of Bayes' theorem that's very useful and very powerful and very applicable. And you should think about this scenario next time you have to go to the doctor. And I know it's hard to do, because when you go to the doctor, usually you're not feeling well, and the last thing you want to do is think about this. But there are actually iPhone apps and other apps out there you can download, and you can put in prior probability of the disease, you can put in the specificity, the sensitivity, 1 minus specificity, and it'll give you back these things for free. So that is all I've got for Bayes' theorem for now anyway. There may be other videos later if people ask questions about homework problems and that sort of thing. There are some more videos coming on counting, so check those out, and we'll see you in the next video.